All right, so we're thinking today about acids and bases, um, and mainly because we've just got done talking about the magic jug, at least in detail, um, and so we need to understand a little bit about acids and bases before we go any further. And so, if we think about what an acid is just a compound that would donate what we call a proton. Proton is an H plus ion. Remember, hydrogen has one proton and one electron, so H plus means it's lost one electron, so it means that all that's left is the proton. So in this case, HCl is donating or giving up or losing one proton, and the water molecule is gaining that proton. When water molecule gains a proton, it becomes what we call hydronium ion, and then we're left with the chloride ion from the HCl, the hydrochloric acid. All right, so we have the acid, the HCl, that donated the proton or gave up the proton, and we have the water that gained the proton, formed hydronium ion. And it turns out that whenever you have a lot of H plus around, it can cause reactions to occur. It can cause things to dissolve. It's what we would call, or what we're going to refer to as an acidic solution, is when we have a lot of H3O hanging around. And the types of acids that we're going to run into, excuse me, first are going to be the strong acids, where we have things like hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, perchloric acid. Notice what each of these compounds has first. It has a hydrogen first in the formula. That's one way to tell that you might have or might be dealing with an acid, is that you've got that hydrogen there. And so these are what we'd call the 6 strong acids. Anytime they're around or they're in water, they're going to give away all the protons that they possibly can. That doesn't mean that every hydrogen in the compound necessarily will be given up, but at least each of these will at least give up one proton whenever they're in solution, and it will give all of it up, 100%. All right? Not all acids are going to be like that. Anything that's not one of those 6 strong acids are going to be what we're going to call a weak acid. You can see here acetic acid and hydrofluoric acid. They're highlighted. Acetic acid is what the sour tasting part of vinegar. So if you've ever had vinegar, you certainly have had acetic acid, and you most likely have had vinegar. And that first proton in the formula is the one that it would donate, but it only donates a little bit of it, maybe like 5% of it, 10% of it at most, unlike those strong acids above it, which donate 100% of its protons. Hydrofluoric acid is a notable one. You might have noticed hydrochloric, hydrobromic, hydroiodic. Those are all the halogens. Those anions are halogen species. You might have said, well, what about fluorine? But it turns out that hydrofluoric acid is a weak acid, only donates a small portion of its protons that are available whenever it's in solution. So those two, and any other thing that would be considered an acid, we would consider it to be a weak acid because it's not one of the 6 strong acids above. You might notice on the right the bases. We're going to get to bases. Bases are going to be things that will accept protons. So when we talk about something giving up a proton, there's got to be something there to take it. It's sort of like in a redox reaction. If something is going to donate or give up an electron, there's got to be something there to take it. If something's going to give up a proton, like in the reaction here, the water is doing, there has to be something around that's going to take up that proton. And in this case, the NH3, the ammonia, is going to be doing that. Now, water would be acting like an acid because it's donating a proton. The ammonia would be acting as a base because it's accepting the proton that's been donated by the water. Okay. Now, I want you to notice that whenever a base reacts, right, with water, it produces hydroxide ion. We said an acid, when it reacts with water, produces hydronium ion. A base, when it reacts with water, produces hydroxide ion. All right. And hydroxide ion is a very, very strong base. All right. So we're producing that strong base in solution, and that strong base would react with any protons that were available or any hydronium to neutralize it. So here we have sodium hydroxide, lithium hydroxide, potassium, calcium, barium, really pretty much anything that's got hydroxide along with it. And what I mean by anything, I mean any ionic compound that has hydroxide as part of it. Generally, we are going to consider to be a strong base. They're going to take up all of the protons that are available. Now, ammonia was our example. Ammonia is a weak base. It's only going to take up some of the protons that are available. Not all of it. Not all of them. So we call ammonia a weak base. And we can measure the amount of acidity that's present. We do that by using something called the pH scale, where pH is minus the logarithm of the concentration of H3O. All right? And so when we talk about concentration, we talk about how much of that H3O is present in solution. It's not really important that we understand what concentration is. Just know it's a measure of how much of something is present dissolved in a liquid. And so we can take the minus log of the H3O concentration, the hydronium, and that's going to give us a number somewhere between 0 to 14 whenever we're dealing with water as the substance that's dissolving the acid or the base. And so we're going to get this number from 0 to 14, and whenever the pH is exactly equal 7, we're going to be considered, the solution is going to be considered neutral, where the amount of hydronium ion is equal to the amount of hydroxide ion. When the pH is lower than 7, we're going to consider the solution to be acidic. That's where the amount of hydronium ion is greater than the amount of hydroxide ion that's in solution. And then when the pH is greater than 7, we're going to consider that solution to be basic. And that's where the amount of hydronium ion is going to be less than the amount of hydroxide ion that's present in that solution. Now, you can measure basicity as well, and that is using a hydroxide ion, which this is going to sort of be counter to the pH scale. And so if we measure the pOH, we're going to just take the minus the log of the amount of hydroxide ion that's in solution, and the pOH can range from 0 to 14 as well. And then when we have those two things together, pH plus pOH, when we add those two things together, it's going to add up to equal 14. All right, so if we have something very acidic, like at a pH of 1, the pOH would be 13. All right, so high pOH means it's acidic solution. Low pH means it's acidic solution. So they're sort of counter to one another. Likewise, if we had a pH of 13, which we would consider very basic, the pOH would be 1. So low pOH means basic, low pH means acidic. They're sort of opposite or reverse of one another. Now, we want to talk about something called an indicator, where an indicator is just a compound that changes colors whenever they lose or they gain a proton. Whenever it's in acidic versus basic solution, it will have a different color. And the one that we have here on the screen is what we call phenolphthalein. Phenolphthalein is clear when it's dissolved in solution. But whenever you adjust the pH, whenever you make it more basic, whenever you remove a proton, okay, phenolphthalein will act as an acid and it will give up that proton, and whatever base is present will pick that proton up. And when that happens, all right, the compound will rearrange its structure, and when it rearranges its structure, it suddenly will end up having a color that's pink. So if you ever had chemistry before and you did titration and you noticed or you stopped the titration whenever the solution went from clear to pink color, that was because you had phenolphthalein present in that solution, and you got to the point where it was basic enough that phenolphthalein would donate its proton. And when it donates its proton, it turns pink, and that's how we would know to stop the titration. In this case, we just want to understand that phenolphthalein goes from colorless to very strongly pink color whenever the pH becomes basic, whenever the pH gets above 7. Between 7 and 10 is where it will transition. And you can see there are a number of different compounds that have been discovered that have different colors depending on what the pH range would be. The top scale on this chart shows the pH. All right, and on the left side it shows the different indicators showing the pH at which it's a different color. And if you look down for phenolphthalein, it's colorless up until a pH of right around 8. And then when you get the pH to about 10, it's a brilliant pink color. If we would think about something like methyl violet at a pH of 0.5 or 1 would be yellow, but when we get to a pH of 2 would be purple. Now there are a number of different uses for these pH indicators. Where we see them a lot is we see them in chemical demonstrations, because there are lots of brilliant bright colors involved with indicating pH with a protonation or deprotonation of a compound. And so one of these is you can turn what we call the demonstration of water into wine, and you can do this a number of different ways. And I'm going to show you 2 different ways you might be able to do it here with 2 different types of compounds, 2 different types of pH indicators. But we have a solution that's strongly basic, has a pH much, much greater than 7. So maybe it would have a pH of 13. That would be a pOH of 1. In both cases indicating the solution strongly basic. In one of these beakers, I'm going to put phenolphthalein. I put it there as a pinkish color, although it's not pink. At the time when you put it in there, it'll be just a couple drops of clear solution. And I'm going to put thymolphthalein in the other beaker. Both of these, whenever you use them, they could pass for wine. I'm going to be honest, I don't think either one of them look like wine. Whenever this demo happens, I think there are other better choices, and you will see that or have seen that in the magic beaker or the magic jug experiment demonstration. So when we take that solution, that sodium hydroxide solution that's highly basic, and we add it to the phenolphthalein and the thymolphthalein, that water now looks very bright pink or looks very bright blue, which I guess would come off as possibly looking like wine. I don't think either one of them really look like wine that way. I think one looks like Kool-Aid and one looks like Gatorade, maybe, something like that. But, I mean, everyone has a different thought about that. But basically, you're seeing a clear solution turn to a color. All right, colorless solution turn to a solution that has some color to it. And that's a dramatic change that most people are very impressed by. I would tell you, I post these on Facebook. I've gotten an enormous amount of feedback from people that have watched me do experiments like this. They just love to see the color changes. And now, we saw this with the magic jug. All right? So the magic jug experiment we saw where... But we didn't just stop with phenolphthalein and thymolphthalein. We had other redox reactions that occur in the magic jug or the magic beaker demonstration. And the first 2 where I think I usually say the first one looks like Kool-Aid. Second one looks like Gatorade, like blue Gatorade. Third one looks like apple juice. Fourth one I say usually looks like wine because it's got that deep, dark color that you would associate with a red wine. And then the last beaker has the thiosulfate in it, and that thiosulfate is colorless, so I usually say, well, we can make water out of it. But those first 2 are solely, phenolphthalein and thymolphthalein, are solely due to the fact that there's sodium hydroxide in that beaker to begin with, in the beaker that we're pouring from to begin with. In the other 2, there's just a little bit of phenolphthalein solution and thymolphthalein solution. And whenever that basic solution comes along, those change color. The others are redox reactions, and you can see me describe those in the video where I do the magic beaker demonstration. So there's no need for me to rehash them, but those first 2 are the result of acid-base. Those redox reactions wouldn't occur without acids and bases as well, and you can see there's hydrochloric acid that's present in those beakers to make those redox reactions go. So, the acid-base stuff is all over the place. It's involved in almost everything, so it's important that we understand a little bit about that. Okay, so you're going to see this. You're going to see the There's another video talking about how to produce photons and heat and what that means for a demonstration. And there are going to be 2 or 3 different demonstration videos for you to watch for this week. So have a good week. Look forward to you'll look forward to your exam that'll come next Monday. And that will be on all the material that we've covered. So Lewis structures, acid base, production of photons, all the different demonstrations like the magic beaker, the whoosh bottle, the non-burning dollar, all those types of things. So have a great day.